Welcome to Circuit Analysis. Today we're going to be talking about scripting and accessing data from simulations. So here's our circuit from the previous video, and if you remember from before, you can go to Simulator and Manage Data Groups, and you'll see right now we have no data groups. But if we run the simulation, there it is. We can go Manage Data Groups, and now we have this one here, SIMPLIS transient 1, and you can see that over here too. Now if we want to save that, we can go File, Data, Save, and I'm just going to overwrite this test data 1 file here. And what we can do now is close this. We change this value here, then we can rerun it, and we'll have a different capacitor charging curve. And now if we go File, Data, and we load, we can load this other data file, and now we are in the other data. So you can see if you go back over to the schematic and you select a probe here manually, it's showing you the data file that you loaded. Now to access data groups with the scripts, we first want to open up the script reference manual, and we're going to go to page 17, scroll down to the bottom, and this is where it starts with the section accessing simulation data. So we'll go over some of this, but this here tells you about how to access it. You use the group name, colon, and then the variable name, like this, and the group name is the data group that we were just looking at. And then if you just use the colon without the group name, it'll just assume it's the current group. And then to access the points, you put brackets like it's a array. And then if you have multiple runs, like a Monte Carlo or a multi-run analysis, then it's like a multi-dimensional array where the first number gives you the run number, and then the second number gives you the data point within that run. And then you can also leave the first number out to get a data point across multiple runs. And then the next section is just built-in functions. So there's all kinds of built-in functions you can use to manipulate the data, and these functions are not in the scripting language. They're lower level functions that are really fast, so you definitely want to call these functions before you start writing loops in the scripting language, because those are hundreds of times as long. Now we probably want to start by seeing what groups and variables are available, so you can do that with the display command just in the command shell. Now there's actually only a couple signals on here that have anything. There's this 3, and then there's the time. You can see over here length, 10,001 points. And then there's also the ground. And the reason that there's only 3 is because in our simulation setup we have save options probes only. So it's only saving this node really that has the probe on it. And if you click on the wire here, then you can see in the bottom here it will say net equals 3, so that's the name of that. And if you want to fix the name of a net, you can go to Place, Connectors, and Terminal, and you can put that over here. And that one was default named to vout, but you can see that now if you run this again, then now it's named vout, and you can see it's got the little pound or hashtag in front of it. If we want to just get one data point, then we can type the name of the group and the name of the variable. So We have echo here, so it will print it out, and then we have the squiggly brackets around it, so it will evaluate the value. And we're just looking for the first point, 0. And that's going to give us 0 because it starts at 0. And if we want to get the last point, we can do 10,000. And we get almost 10, which is the blue line up here. And if we want to change that and do SIMPLIS tran 3, we can put this back 10,000 and change this to a 3. And that one failed because we actually have to change the variable name to 3 because it wasn't named vout at that point. And now you can see 8.6, so that's this green line. To plot a line, there's two commands. You can use plot and you can use curve. And we can close this. So if we do plot and we do the SIMPLIS tran 3, then it'll plot that curve. And if we do the other curve with plot, then it will plot that as a second tab, so it's by itself, and you can click back and forth on these. And the difference with curve is you can, if we go to this first one here, we can change this plot to curve, and it will add a new curve on top of this plot. So you can use plot for a whole new plot, or curve to keep adding curves on top of the same plot. And you can plot any vector, so you can make your own vector and plot it along on the graph too with any other vectors. Now a lot of times when you want to manipulate the data in these curves, what you're going to want to do is pick out a certain subrange. And what you have to remember when you're trying to do that is that the simulation runs based on a maximum step size. So the points are not all evenly spaced. They could have a much smaller step size depending on how fast the curve was changing at that point when the simulation was running. So to do that, the first thing you want to do a lot of times is use the interp function and interpolate the curve so that it has an evenly spaced number of points. And then you can use that to zoom in on a specific time range. So we're going to start a new script to keep track of what we're doing here. And we're going to start off by interpolating this vout curve and looking just at a middle section. So we'll just create a variable, we'll call it v for our vector, so that we don't have to write this out all the time. And we'll make I be the interpolated value. So here's the interp documentation. And the first parameter is the vector, the second is the number of points, the third is the interpolation order, and the fourth is the mode. And so the interpolation order is the spline that's going to be used to interpolate. So 1 is linear and 2 is like a second order. So this last argument's a little confusing, but we're going to use 1 and 1, which means we're doing an interval. So we're specifying the distance in time between each point as opposed to the number of points. And we're also doing this t over n minus 1. So we're going to do v is our vector, and 100, we'll do 100 microseconds between each point to start off with, and you'll see there'll be very few points. And we have to have no space in between these. We'll do 1 for our order, so it's just a linear interpolation. And then 1 is our options. And then we're going to say plot I. Now we can run this. And we'll see we get our curve here that has these very few points. You can see they're connected here by straight lines. So if we want to make that a little smoother, we can change this to 10 microseconds. Run that again and see it's a lot smoother. If we want to pick out just the middle part of this curve, we can use the range function. And that takes 3 parameters. It's the vector and then the start and the end index. So we can go back to our script. So we'll add in our range here and we'll call it R. And the first thing we're going to give it is I. And then we want to give it the range. And if we look here, let's just get the middle. So we'll say 400 to 600 microseconds. But we have to remember we interpolated it with 10 microseconds per point. So that's going to be 40 to 60 on our index. And then we can change this to R and run it. Now you can see we got 400 to 600 microseconds. Now I want to talk about a special case which I had some trouble figuring out, which is measuring the BH curve for a saturable transformer. So for that, we're going to want to switch back to SIMetrix mode because we can't really model that on SIMPLIS. And we're going to want to place magnetics, and we want a saturable transformer. And we'll just make it a 1-to-1 transformer, and we'll just go with this core because it has a low saturation value. E14 3.5 5R 3C90P. And we're going to place that here, primary, secondary, and then we're going to place a waveform generator. And we'll place a couple resistors, use F5 to rotate them. So we're going to make this resistor 1 ohm so it lets a lot of current flow. And we're going to change the pulse in here. Let's give it 500 micro and we'll have it start at -5 and pulse to 5 volts so it's symmetrical. And now if we run this, we can look up here and plot, add curve, and if we look at the available vectors, we can type T, and we see TX1, and there's no options. There's a bunch of different vectors, but there's nothing for the B or the H. So we'll cancel that. And it turns out the trick is, well, let's rename this. We'll just call it T1. Well, the trick is if you do the F11 window, you have to go in here and use this keep command. And then you have to say the name of your transformer dot lcore and then pound hashtag B and also H, and then that will keep those values now. So if we run it again, then we can go plot, add curve, T. Now we see we have this B and this H. So if we use this XY plot checkbox here, we can do B on the top, H on the bottom. We can label it B-H. And now we've plotted it. We can select these other two curves and press the delete key to get rid of them. And now we see our BH curve. And it's starting to saturate a little bit on the ends. One thing to note is the units of this were a little tricky at first. It turns out that it's in Teslas or milliteslas, so you just have to use the conversion factor if you want Gauss, that there's 10,000 Gauss per Tesla. So one thing to note is that the formulas that you put in, if you go to plot, add curve, here, these are the same formulas that you would type in the command shell or in the scripts. So over here, if we wanted to do the same plot, we could say plot, and then if we want to do x, y, we just do the first thing and then the second thing. So we'd say t1 dot L core B space t1 dot L core H. And then you can see that plotted the same thing. Now that we've talked about plotting full curves, let's talk about how you resolve a curve to a single point, such as the average or the min, max, the frequency, or the peak to peak, or something like that. So for this, let's use the output on our new circuit. So we'll Control X, Control V, move our probe and our connector over here. We'll run this. We'll get rid of our BH curve. And you can see a couple spikes here from the transformer. And we're just going to be using some of those functions that we saw before, starting in the reference manual on page 19 in this long table of functions. And these have links so you can click on them and go get more details on each one. So let's get our script back here. And we'll just delete this and we'll start over. And now that we're in SIMPLIS, there are some slight differences. So like if you click on this node here, it shows at the bottom net equals V out. So there's no pound sign in front of it now. So if we go over here, we can just write echo, use the, we'll start with maximum, so we'll put max. This is just some text, and then we'll put the squiggly brackets and we'll do maximum, which is the function, and then we'll say V out. And if we run this, then we'll see it'll print the maximum here. So I've added a few more functions here. The min, the average, the peak to peak, and the frequency. And I put clear message window at the top. So if we run that, you can see all of those print out for our signal. Now you can combine several of these functions, like you could use the interp function and then the range function to select a specific part of the graph, and then you could use the mean function on top of that to get the average of that, for example. The other thing is you could get a rise time using a couple ranges or a dead time. Let's try for our waveform. We'll zoom in a little more here. Let's try and use the range function to get out just one of these pulses and then try and calculate the fall time of this. We're going to want to have a fair amount of resolution here. So this is 5 microseconds per division. Let's do 0.1 microseconds for our interpolation so we get 50 points per division, and then we'll just cut it out here 495 to 510. So if we go back to our script, we can make a new variable. We'll call it R equals range interp V out. And notice I haven't been specifying the data group here because we're just using the current one. 0.1 microseconds, using 1 for the interpolation order, then our parameters. And that will go from 4950 to 5100. and then we can plot R. Run that. Now we're going to use the x from y function to get a couple of points here, and we'll calculate the difference between those points. So we can go back to our script. We'll let x1 be x from y of R, and we'll just say, let's just go from 6 to 1. We could calculate 90% based on the max and 0, but we'll just go 6, and then if we echo this, we can see we got 2 points, and the first point is 6 right here where it's going up, and then the second point is where it's coming down. So we want to use the second point, and we can do that again for the bottom here at, we'll say 1. So if we copy this, so now we have the time values for when it crosses 1 going up, and 6 going up, and then 6 coming down, and then 1 going down. So we want the second value for 6 and the second value for 1. So it's the second value for 1 minus the second value for 6 is going to give us our fall time. So back to our script, we'll let the fall time be x2, and the second value is index 1 because index 0 is the first value, minus x1, 1. So you can see now we have our fall time here, 2.613 microseconds, from 6 down to 1. And you can use that same method for rise times and measuring different things with the waveforms. So that concludes our overview of accessing and analyzing the simulation data. Thanks for watching.